Dear participants, good morning to all. Uh, Good afternoon to all. It gives me immense pleasure to introduce our esteemed guest for today's online training session. We are fortunate to have Dr. Santosha Rathod sir. He is a scientist at ICR Indian Institute of Rice Research, Hyderabad. Dr. Rathod has significant contribution in the field of modeling and forecasting of agricultural systems, artificial intelligence in agricultural systems, machine learning and optimization techniques, and genomic selection and prediction tools. So today, Dr. Rathod will talk about machine learning techniques for modeling agricultural data. So without further ado, I now hand over the platform to Dr. Santosh Rathod, sir. So platform is yours now, sir.
Thank you for the opportunity and for your nice words. So the participants all are they are all agriculture graduates, or I mean.
Yes, sir. Most of them are agriculture graduates. Some are masters, some are PhD, and even though some
Actually,
are assistant
students, faculties, both are.
Okay. Because the mostly the examples or illustrations what I mean supposed to talk is like I prepared this time series. I don't know whether how much it will be useful to them. So I will try to cover in a broader area. So what are other topics covered, Kapil? Any lectures on time series?
Not sir, only basic regression and correlation.
Okay.
Basic regression.
Okay. Done. So I'll share my screen now.
Yes, sir.
The screen is visible, right?
Yes, sir. It is visible.
Good afternoon, friends. As today I'm going to talk on application of artificial intelligence techniques in agricultural data, in specific to the time series data, and I'll just introduce some more applications of this in genomic prediction. Suppose if some breeders are there in this group. So basically, I will cover what are different time series models and how these AI models they are different from the time series models. And time series models also we have like different models under what conditions or what kind of assumptions we need to go for which models. And sometimes what happens like data contains both linear and non-linear parts. Under such condition, we need to go for hybridization, or we call it as a two-stage modeling. That also we're going to cover, and I will cover with some examples, and then we can do some practicals for half an hour, and then we can conclude the session. Right? See, as maybe this is last day of the training program, you all know like what are different kinds of data and how the data are generated or how they are collected. So based on the generation of the data, so we can we divide them into a primary data and secondary data. So these data can be generated either from experiments, either you can collect it from the you can conduct a survey, or you can collect the data, and sometimes you collect the data from the published resources also, right? So again, like if the data is recorded over the different period of time, suppose the temperature data we record over the daily or monthly or yearly basis, and this kind of sequence data over the period of time, this kind of data we call them as a time series data. And sometimes what happens for a particular time period, you collect the data for 10 locations, or suppose say for 5 you conduct the multi-location for a particular season, you conduct the multi-location trial for 5 location. Such kind of data we call them as a special data. But sometimes what happens, we collect the data for both space and time. Such data we call them as a spatial temporal time series data. So as I said in the beginning, in this class we try to focus more on the time series. And in time series, whenever we get the data, generally like in a classical or traditional time series, we take a data and you go for the prediction or trend or other forecasting, right? So suppose your data is like a short data depends on only let us say for short duration of time, let us say only on 1 lag or 2 lag. Under such condition, we need to go for the simple, I mean exponential or moving average models. And suppose the data is depends on only on yesterday's data, such kind of data we can model using single, double, or simple exponential smoothing or triple exponential smoothing methods. And suppose if you want to see the trend in the data, how the data is behaving from last 50 years or 60 years or over the period of time. Suppose it is a daily data like 1 year, how is the trend in the data? And then you can go for the trend. And this time series has a 4 components: seasonal components, trend components, cyclical and irregular components. So whenever you go for the forecasting, we need to decompose these components, and each components you can study separately. Like the trend is one of the component, and it is the most predominantly occurred in the data where we have like a less than a year or a yearly data. And once you believe that yes, this data has some kind of correlation in it, then we need to go for the time series data. And can anybody tell me what is the difference between regression and time series models? What are the regression models? Under what condition we go for regression modeling? Why you go for regression? Am I audible?
Yes, sir. Yes, sir. You're audible.
Then anybody tell me what is the difference between regression and time series? Under what condition you go for regression and under what condition you go for time series?
Actually, in time series data set, time observation is dependent on time over the time, and in case of regression, is independent variable is dependent on some other independent variables.
So that you know very well. So I'm not having. Okay, as he said, like when you have observations under consideration are independent in nature, and like then we under such condition we go for the regression modeling. And suppose the data under consideration is autocorrelated or self-correlated. So let us say today's temperature depends on yesterday's temperature and day before yesterday's temperature. In such condition, we need to go for the time series model. So we cannot go for the regression models under such condition. So to test that, we have a test called box PS test, and whenever we get the data, if you want to go for the time series models, it is necessary to see the autocorrelation texture in that. That it can be done by box PS test. And so once the autocorrelation is confirmed, then we need to go for the time series. Another assumption of time series modeling is the stationary process. The stationary means, sorry, whenever we suppose we have a 50 observations, and suppose we break these observations into 5 parts, and these parts and 5 parts, if you calculate the mean and variance, and these mean and variance are constant over a period of time, and such series we call them as a stationary process or a stationary series. So whenever we go for the time series modeling, the data should be stationary in nature. To test the stationary, we have the test called augmented Dickey-Fuller test, right? This test, these two conditions must be satisfied, then only.
Sir, please unmute yourself because voice is not coming. Sir, please unmute yourself.
I think your video is stuck, sir. Screen share is working properly, but your video is not.
Please enable me to share the screen.
Okay.
Okay.
Yes, sir.
Okay. As in time series, there are different models. As I was talking about this ARIMA model. So ARIMA model has two parts. One is autoregressive integrated moving, autoregressive part, and the one is moving average part. In the autoregressive part, we see the observations, they are lag. The original observations are lagged in nature, and we see the regression in dependency in them. That is called as autoregressive term. And in case of moving average part, you see the error terms are dependent in nature. So this part we call them as the moving average part. And this model is autoregressive integrated moving average model. And suppose the term integration is, again, I said, the stationarity. Whenever the model under data under considering stationary, then only AR and MA part will be there. And whenever your data is not stationary, then what we can do is we just difference the series, first differencing or second differencing, and we convert the stationary, non-stationary data into the stationary data. And then this I term will add, that is integration. And then the model will become autoregressive integrated moving average model. So as I was saying, like whenever we have the time series under consideration, we need to see the autocorrelation in it. That can be tested by using Wasp-based test. And once the autocorrelation is confirmed, then we need to go for the stationarity, like the mean and variance over the period of time, they should be constant. And then once these two parts are done, then like I was saying, the time series, they dependence on the lags, and we need to identify what is the significant lag for the model. And for that, we can see the two functions can be used: autocorrelation function and partial autocorrelation function. This partial autocorrelation function can be used to identify the autoregressive orders, and ACF can be used to identify the moving average orders. If you see the significant spikes in this graph, we have one spike which is significant, and in the second graph, that is PSF, we have one spike significant, that is crossing the blue line. Then we can say in this we can one is a AR order and one is a moving average order, and this is like this we can identify the model orders. And once the model orders are identified, then we can estimate the models. Like in case of any statistical models, we need to estimate the parameters of the model. That can be estimated using ordinary least square or maximum likelihood estimation methods. And the another method of identification, we just keep on trying to change the model orders, and then see the AIC and BAC values of the model. Wherever we get the lowest AIC BAC value, that model you can finalize it as the final ARIMA model. Once this is orders are identified, then you need to estimate the models. And once the models are estimated, then we need to go for the diagnostic checking. Like in case of any statistical model, we assume that data under consideration is normal in nature, and given the residuals are follows, they also should come under the normalization. So to do that, we have to see the normalization of the data, or else we can simply check the autocorrelation pattern present in the data set, residuals. And once the residuals don't have any autocorrelation present in them, then we can discard the residuals and we can consider that as a final model, and then we can go for the forecasting. So this is about the ARIMA model, and not only ARIMA, this five or six steps, they are common for any time series model. Whenever you have a time series under consideration, we need to see the autocorrelation, stationarity, model order identification. Once the orders are identified, then we have to estimate the models. Once the models are estimated, then we need to go for the diagnostic checking, and the final models all are fine, then we need to go for the forecasting. So this autoregressive, this ARIMA model will be useful when you have the shorter lags, like suppose say 4 or 5 lags, they are dependent. But sometimes what happens, your data under consideration has a long memory. So let us say today's price depends on last 30 days price or 40 days price or one year or 2 year price. Such kind of data cannot be modeled using the ARIMA model. So they have to be modeled using the RPM. RPM is autoregressive fractionally integrated moving average model. So the difference term will become the fractional term. This model is same as ARIMA model. The only difference is this model is like it has a fractional term in it. The D is ranges between 0 to 0.5, but whereas in case of your ARIMA model, it is a discrete number that is ranges 1, 2, or second or third order difference. But in case of RPM model, it will be ranging in the fraction. So the major like whenever simply what you can do is whenever we have the data, that data we can plot the autocorrelation function, and if you see the lags, if the lags are decaying gradually or exponentially, then you can say the data under consideration has a long memory. For example, if you see this data, this is a trailing data. If you see here up to 200 years, the data is like they has a lags, significant lags long memory up to 200 lakhs, or that you can say the tree rings, they depend on the 200-year back data. So such data we cannot model using the autoregression model. We need to go for the long memory models. And to test that, we have the test called rescaled range test, that is R by S test. And if you do this test and if the ranges, the D value comes between 0 to 0.5, then this model you can say it is the data contains a long memory. And suppose sometimes what happens, D comes 0.6 or 0.7, 0.5 to 1. Under that condition also data will be your long memory, but that is a non-stationary. So non-stationary and long memory. Then we need to difference the data, and then we need to go for the long memory model. And the next step is like stationarity. So as I was saying, like whenever we have the data for any time series model, we need to see the stationarity test that can be done by using the augmented decay flow test. Once these two conditions are satisfied, then we have to identify the model orders that can be identified using AAC and PAC, and we can find out the significant lags by using the AAC and BAC values. And estimation, as in case of Arima, we can estimate the model based on the maximum likelihood estimation method, but here GPH estimator is most commonly used, and similarly diagnostic checking and forecasting can be done as we did in Arima model. And next we have this generalized linear models. Sometimes what happens, we have if any entomologists are there in this group, sometimes what we have a light trap data, we collect the data, we install the light trap in the field, and we collect the data daily over a period of time. And such data will be like a correlated, and but they have a discrete observation, they are not continuous. But in case of experimental field, what we do is we take this data and we do the square root transformation and we do the analysis. Whenever we have a direct distribution like poison or in this negative animal distribution with us, you need to go for the data transformation and do the modeling. And there are paper where if you do the transformation forcefully and do the modeling, and if you do for the same data, if you do not do the transformation and you do the GLM modeling, the GLM modeling has performed better compared to the your transformed data. So whenever you have a count data, suppose let us say number of people educated, number of people unemployed, number of road accidents, number of insect waste, such data we should go for the count time series models, and they comes under the generalized linear model. And to model such kind of data, we have a in-Garch model, that is integrated integer based Garch model, and this model can employ for the data where we have the count observations, right? So I'm just giving the highlights of the model under what condition we can go for which kind of what models. And here we have another time series where we have intervention. Suppose for example, the government of India has announced a lockdown during 2020 March month. But there are because of that lockdown, there are sudden decrease or increase in the sale or increase in the supply of the agricultural commodities, and that lead to the major change in the price of the data. Under such condition, if such kind of interventions are there in the data, we cannot model them using the Arima model. We need to go for the time series intervention models. And the Arima intervention model is one of the example for that. Whenever we have some policy changes, if we want to see the impact of some schemes by the government, and such data can be modeled using the Arima intervention model. And then we have a spatio-temporal model, as I was explaining in the beginning. Spatio-temporal data, suppose you have the temperature data over a period of both space and time, and such kind of data cannot be modeled using the Arima model. If you want to incorporate the neighborhood effect in the model, we need to go for the Sturma model. And in this case of Sturma model, the model building is almost like same as Arima model. The only difference is here we see the spatio-temporal correlation by using multivariate box-based test. And once you observe that there is a data under both space and time, or they are spatially correlated, then we need to incorporate the spatial information in the data by using the weight matrices. These weight matrices can be constructed using different methods. Here we have in earlier papers, we have dealt with different weighing schemes like uniform weight matrix, equity and distance, KNN based, fuzzy logic based, and correlated weight matrices. This I will show in the examples. And this again, as I was saying, like you can identify the model orders based on the ACM and PSM. Similarly, in case of Sturma, we have space-time autocorrelation function and space-time partial autocorrelation functions. Once the model orders are estimated, then we need to orders are identified, then we need to estimate them by using maximum likelihood estimation methods, or else suppose some machine learning optimization techniques like GA, PSO, like that we did in our previous studies, that also can be done. Once the model orders are estimated, as a regular practice, we need to go for the diagnostic checking, and that can be done using multivariate box-based test. And once all these conditions are satisfied, then we need to go for the forecasting. And I was saying, like, we need to construct the special weight matrix to incorporate in the model. Suppose this is a data of temperature data of North Karnataka, where we have considered the 9 districts temperature data, and this is the map of the data under consideration. If you see the map, suppose for example, for the first district, the first location, the immediate neighbors are 2 and 8. So what we have done is we have assigned equal 1 by 2. Suppose 2 locations are immediate neighbor of the first location, 2 and 8. Then I have done 1 by 2 and 0.5 weights has been assigned to these 2 districts. Similarly, for the third, like for the second district 2, these 3, 7, 8, they are 1 and 3, they are immediate neighbors, and for that I have assigned 0.5, 0.5. And for if you see for the second lag, 3, 6, 7 are the immediate neighbors, 3, 6, and 7. So 3, 6, 7, 1 by 3, you make it 1 by 3, 0.3, 0.3, and 0.3. Like this, we can assign the uniform weight matrix. And since uniform weight matrix does not consider the heterogeneity of the location, we can go for some other weight matrix weighting schemes like fuzzy schemes or Euclidean distance or correlated weight matrices also. So this is all about the time series data. So in the, here I have mentioned about 5 situations where if we have short-term time series data, we need to go for the RIMA model. Whenever you have a long-term data, long memory data, we need to go for the RPMA model. Whenever we have a count data, we can go for the GLM or count time series models. And whenever we have a spatial temporal data, we need to go for a STARMA model. And whenever we have a let us say data under intervention or certain policy changes or weather calamities and all, then we need to go for the intervention or interrupted time series models. So this is all about the time series. And till now, if you have any doubt, you can feel free to contact me. So if you have any doubt, I will clarify, and then we can move to the artificial intelligence parts. Any doubt, please ask. Any doubt?
Hello, good afternoon, sir.
Yeah, good afternoon, please. Yeah, Sanket.
Sir, Sanket here. Sir,
Tell me.
Sir, which forecasting model for vegetable forecasting? Price forecasting, sir. Vegetable price forecasting. Which model can be used, sir? Specific model, sir.
Again, it depends. As I was saying, like if you have a lags, like short-term lag, then you can go for the RIMA. And if it is a linear data under consideration linear, then we can go for a RIMA model. Again, it has a long memory, we can go for the price also. Sometimes in one of our paper, like the master price we have taken, and that data has a long memory. So under such condition, we need to go for the long memory model. And suppose again the data is highly nonlinear and complex in nature, then we need to go for the machine learning model. So it depends. If first thing is we need to plot the data, and you have to see the basic time series property, and according to nature of the properties of the data, we can go for the suitable models. Okay, so okay, now the next thing is we see once this 5 time series are, these are all the basic, then the major point that today talk is artificial intelligence. As everybody knows, like nowadays, like in most of the cases, like most of the field, we implement this artificial intelligence models in all the field. And so why this artificial intelligence has arrived is, like whenever you have a complexity in the data set or your normal statistical models, they don't work under the assumptions of the see. When statistical models, they are work under some certain assumptions. If these assumptions does not satisfy or or they they deviate the assumptions. So then we need to go for non-parametric models or the machine learning models. So this artificial intelligence is a field of science that creates machines or devices that can mimic the intelligent behavior of the human. So this is a major concept of artificial intelligence. In the human brain contains many neurons, and these neurons they have the power of parallel processing. And the artificial intelligence community they wanted to develop artificial brain or network so that can mimic the human behavior. And basically, this artificial intelligence has motivated from the human behavior, the human learning system, and from there the science has evolved. And similar, like most of the time we use the term AI and ML as a similar. So, but if you clearly see the difference, the ML is a part of the AI that provides the computers with the ability to learn without being explicitly programmed every time. So we can say machine learning, they are the part of the artificial intelligence. Yes. And if you see here, he is the person Arthur Shamil who first engineered the checker learning board. Based on that, only the AI concept has derived, and he has explained the theory that the person can learn based on the mistakes made of his self-learning, and from that which he learns, and by the more he becomes the experience, and that will lead to a better accuracy of the model. So by this concept, this artificial intelligence has started, and the author, this Samuel Arthur, we call him also a father in the artificial intelligence. And if you see, like in 10 years back, if you see the development in the machine learning, like earlier people used to call machine learning as a black box. Like we just give some input data and it will give you the output data. So nowadays it is not, that is not the case, because it involves a lot of programming and probability and statistics, because most of the algorithms they learn based on the some statistical theories. And so we can call the machine learning as a mixture of programming and is a probability and the statistics. Because if you see the back propagation algorithm or any other algorithm, they all derived based on the some derivations, or the derivatives minima maxima, or based on the some probability or learning derivative. For example, your Bayesian neural network, they all derived from the probability based statistics. So we can clearly say this machine learning is not at all a black box. We can easily, like, you can calculate the weights, and you can estimate the models based on the probability and statistical theories. And if you see the clear difference here, so the output is your artificial intelligence, and the engine or your programming is your machine learning. So this is the clear difference between artificial intelligence and the machine learning. So when I say the learn, so the learning can be done in 3 ways. There are 3 classes of learning: supervised learning, unsupervised learning, and reinforcement learning. So whenever, suppose that if I say the example, like teacher-student learning, so this is called as a supervised learning. Now I am taking the class and you are listening to me. This kind of learning, we call it as a supervised learning, where in case of, suppose if I explain it the modeling term, like input vector along with the target vectors we give in the model, then this model will become your supervised model. And suppose you don't have a target variables, you do yourself, you do self-study and learning from your own experience. This kind of models, we call them as unsupervised models. And based on the availability of the target variable and input variable, we need to choose the suitable models. And sometimes for the some data set, we have the for the target variable, and for the some data we don't have a target variable. So such learning we call it as a reinforcement learning. It is a mixture of both supervised as well as unsupervised learning, right? So if some part you do the self-study, and some you take the help of your friends or a teacher. Such kind of learning we call it as a reinforcement learning. And basically, this machine learning can be classified into 2 parts. In fact, 3 parts, like classification, data mining, and regression. So, but broadly, data mining, pattern recognition, they all comes under the classification. So classification also most commonly used in this image processing of nowadays, the phenomics and other things we are doing. And under such condition, the machine learning classification is most commonly used. And for time series or other problems like cause and effect regression, cause and effect relationship model, we need to go for the regression models. And regression, one of the time series comes under the regression of the machine learning, right? So basically, the machine learning broadly can classify them into classification part and regression, classification problem and regression problem. Classification, when you want to divide them into, suppose if you want to see the forest cover, if you want to divide the rice crop and other crop by your NDVI or other data, then you can go for the classification algorithms. And suppose you want to predict based on some data sets, you want to predict the feature observations, or if you want to have a cause and effect relationship, then you need to go for the regression machine learning, right? As I was saying, like the neural network, the artificial neural network is the fundamental, and it is the most important or most popular artificial intelligence technique in technique. And this technique has motivated from the human brain. And if you see, like our brain has composed of 10 to the power 11 neurons, and these neurons has all the parallel processing. So if you are sitting here also, we can do a parallel processing in your mind, and our mind is so powerful, like we can compute several things in our mind. So this neural network also has the same concept, and it is derived from the biological neuron. So if you compare this neural network with the human brain neuron, so it has a 3 parts: dendrites. So dendrites, they are the entry points. The information will be fed into our mind in terms of dendrites, and this information will go to the cell body, that is your activation functions or hidden nodes, hidden function or your hidden layer, where your information will be processed, and finally the axon terminals, where the output will be coming out. And this output, this axon terminal, they may act as again the neuron or input to the for the neurons. So basically, like in case of neural network also, we have 3 layers: input layer, hidden layer, and output layer. And this all derived from the inspiration from the human brain, where dendrite, cell body, and axon terminals, where information will be processed in the cell body. So, and if you see the first artificial intelligence or machine learning model, that is your McCullough and Pitts model. So before like 1943, this model has came, and this is a combination of, like, they have proposed that this is a combination of your input variables, and if you assign some weights to the inputs, and if you sum the inputs and the weights, and the finally output will come. And this they call it as a threshold logic gate. And see, suppose you just see Wi into this, multiply the input ii and w1. So if this becomes your weight, this combination, if you sum all this combination, if this combination of this weight, if it crosses a suppose some threshold level, then we can say yes, we have to execute the output. So this is called as a threshold logic gate, and McCullough and Pitts. This also can be called as a McCullough and Pitts model. This is the first neural network model, and if I explain it with an example, see, this does not have any like any distribution or any normality, any assumption. It is based on the totally based on the assumptions. Our own assumptions are convenient. Suppose say today I want to watch that switch on the TV or not. So what are the different conditions when I will switch on the TV? So first condition could be like if I like the IPL more. So if IPL is on, IPL is there, then I can switch on the TV. And second possibilities could be like if it is a suppose if it is a practice match, then I care less for the practice match, so I can skip this match and I do not switch on the TV. And if suppose I like the practice match, then also I can switch on the TV. And again, since I am a big fan of Mumbai Indians, like if the Mumbai Indians is playing, again I can switch on the TV. So and so on, you can see the different these possibilities, and you can assign the weights to the each possibilities. And if this weight it crosses the summation of this all weights and my inputs, if it crosses suppose certain levels, that threshold level theta, then we can execute, I can switch on the TV. So this is how the artificial intelligence will work. So this is all based on the data. I mean, it is a data-driven approach. It is based on the different possibilities it will consider, and it will execute the output. And suppose in 1950, one model came, that is perceptron model. So this is same as McCullough and Pitts model, but only thing the difference is here they have added the bias term. And suppose I will switch on the TV, and suppose my daughter is not feeling well, I have to take her to the hospital. So what I will do is I will just shut the TV and I will go to the hospital. So that also can be added in terms of bias term. And this is all like all the combinations. This all combination we consider in the artificial intelligence and we build the model. So only this artificial intelligence, they are very flexible, and they will give us the output based on what kind of input and the tuning parameter you are providing into the model. Right? This is about the artificial intelligence. Like that, we have different models in the AI. And the artificial neural network is one of the most popular model. And as I was saying, it has 3 layers: input layer, hidden layer, and output layer. The information will go into the input layer, and the information will be processed in hidden layer, and the output will be coming out from the output layer. So how this information will be processed? Like it is depend the hidden layer. They will assign the activation function. Like suppose you have a linear data, then we can go for the activation linear unit or some other activation function. Suppose you have a count data, we need to assign the sigma model activation function. And this activation function, hidden layer, will help us to assign different kind of non-linearity to the data, and it will process the data in the hidden layer, and it will give the output layer. So the basically input layers and suppose your data, if you want to do some transformation or normality, then you can convert the transform the data into before input layer, and you can that data you can feed into the input layer. And once the output comes, that output again you can transform back to your original variable, and you can see the comparison. And in hidden layer, the information will be processed by using the activation function. The once the information will be processed, that information will go to the output layer, and that will be our final model output. And see, there are like we have a simple neural network, then we have a deep learning neural network. As I was saying, like whenever you have a single neural hidden layer, then those models we call them as a simple neural network. And whenever you have more than one hidden layer in the model, if you see this orange color, we have 4 hidden layers here, and this kind of network we call them as a deep learning. So difference between the simple neural network and deep learning is only where we have a different, we have more than one hidden layer in the hidden layer, and in case of simple neural network, we have only one hidden layer. Yes, as I was saying, like activation function, we have a different activation function. If suppose your data is linear, you can go for identity activation function. Whenever your data is count or like it is categorical data, we need to go for sigma model activation function. Whenever your data is highly non-linear, or it is a sine or cos wave function, then we need to go for tan and arcsine and this sine transformation function. And whenever your data assumed to be normal, then you can go for the radial basis function or Gaussian function. And for the continuous data, we can go for the ELU or RELU, that exponential linear unit or rectified exponential linear unit can be used for the use as activation function in the model. And the backpropagation algorithm, as in case of simple regression or your time series, we use maximum likelihood estimation method. But in case of neural network or machine learning, we use backpropagation algorithm for the time series data. So this is simply like it will take the very actual and predicted values, and it will compute the first error. So if you see it will define the function in terms of error term, that is, it is a half of the summation of yi, it is your actual observation, dj is your desired observation. It will take the square summation of this, and it will compute the maxima and minima. Yes, compute maxima and minima, and for the second derivative. For the secondary derivative, whenever it attains the minima, that weight it will take it as a final weight, and it will assign to the network, and again it will take, it will go to the next weight. So like this, we cannot say the neural network are black box. We can compute the weight in each steps, and we can do the modeling. And if you want to learn more about this algorithm, you can visit this paper, the King algorithm back proportion. This is published in the Nature journal. Then this neural network, how we can like implementing time series data is, the first thing is, as I was saying, like we need to go for the box Jenkinson autocorrelation test. And whenever the data under consideration is linear or non, because most of the time the neural network we use for the nonlinear data, and the nonlinearity can be tested using the BDS test. BDS is the name of the scientist. This test is available in F nonlinear patches, and once it is confirmed, then we need to go for the artificial neural network. And in case of any modeling, not only artificial neural network or machine learning or time series, in any sense, we need to divide the data into, as I was saying, it is a self-learning or it is a different learning. We need to divide the data into a different part, that training parts and testing parts and validation parts. Suppose in the ratio of 90:10 or 85 90:5:5, And in the training data, we need to build the model, and for the testing data or validation data, we need to validate our developed model. So like that, we can divide the data prior to the modeling. Now, once the data is divided, you can do the normalization or other transformation to the data if it is required. Otherwise, you can directly fed the data into the input layer, and you can get the output. And you can choose the suitable activation function based on the nature of the data. And finally, once it is once the model is built, then we can compute the error in terms of mean absolute percentage error or mean square error, and you can compare the model performance with respect to some other models. And there is one test called Diebold Merino test. Suppose like if you want to see the significance performance of the model, the Diebold Merino test is most important, because suppose we have two models like ARIMA model and ENN model. And ARIMA model is given me 10.1 error, 10.1 RMSE, and the ENN model has given me 10.2. Then which model you compare? Which model you will use? So obviously we will say that yes, the model is giving me lesser error, that is 10.1, that is neural network model. That model only I'm going to use. But sometimes what happens, the cost of building the model will be more than the other models. Under such condition, we need to see the cost also based on the, if suppose there is no significant difference in the performance of the model, then we can choose the model which is given as the less cost to build the model. So that can be tested by using the Diebold and Merino test. So DM test is available in F nonlinear package. Maybe it is in forecast package. So we can use this package, and you can compute the model significant performance. So next, in case of artificial intelligence, we have a most commonly used model is a support vector machine. So neural network can be mostly used for the situations where we have a this unsupervised modeling, or when we don't have a target variable. Under such condition, we need to go for the neural network. But in case of support vector regression, we need to have the target variable. Whenever we have the target variables, we need to go for the support vector machines. And suppose if we have the data dimension is less, under such condition also support vector machines are most powerful compared to the artificial neural network. So if you see here, this I have two parts here, the dark part and the lighter one. So I can divide this data into a different by using different margin classifier. So I can classify this data into these many possible combinations by using drawing the different lines. But what support vector regression will do is it will give us the thickness of the margin, and this margin will help us to have only one classifier. And by employing support vectors, these two darker points, or these points you can call them as a support vectors. It will give, by employing the support vectors, it will give us the classifier thickness. It will increase thickness of the classifier, and we can have only one classifier to divide the data. So the basic idea in support vector machine is to transform the original data into a high dimensional feature space, and it will carry out the linear classification in the or linear regression in the data. As I was saying, like it will assign the artificial variables into the model, and it will increase the data dimension. So your nonlinear data will become the linear problem, and then the model can be built. So if you see this graph, so you have to, like, this is a nonlinear problem. If you increase the dimension of the data, this problem can be made into the linear problem. So this is the basic idea of the support vector regression. And if you see here, when you have a x1 and x2 variable, this x1 and x2 can be written in the quadratic discriminant function in the form of a1 x1 a2 x2 a3 x1 square a4 x2 square, and so on. And this form can be transformed into a linear space by taking the like for x1 x2 we assign the variable z5, and this is called as a linear discriminant function. This linear discriminant function can be used whenever you have a less dimension. But suppose when you have n to the power n, or if you have infinite number of data, it's very difficult to go for the linear discriminant function. So we need to go for the optimization problem. So this we need to choose optimization can be done by linear programming or by the quadratic optimization function. This all, like, we can, if you have someone is more interested, you can read those. I just skip this part now. Like in case of neural network, we have an activation function. Here we have a kernel function. So kernel function in support vector machine, the kernel function will help us to assign the non-linearity to the model, and it will do the modeling. So it is same like activation function. In case of support vector machine, we have a kernel function, right? And we have different kernel function: linear support vector machine, polynomial of degree, different polynomial function. Then the most commonly used one is the radial basic function, and this function can be used to construct the support vector machine model. So this is the most commonly used radial basis function, kernel trick function in time series. The major difference between your neural network and support regression is, in case of error minimization, you have two parts. And in case of but in case of this supported regression, you have a loss function also. This loss function depends on your nature of the data. You can assign the exponential loss function. You can assign the root mean square error. You can assign the mean square error based on the nature of the data. You can assign the loss function. So this is the major difference between your neural network and supported regression, where you have regular this function you call as a regularized function, and in case of neural network we have empirical risk function. This is the only difference between the error minimization principle of neural network and your this artificial neural network. But the empirical risk minimization, that is your neural network, they will not give us it will not give us a generalized error, and it will give us a larger confidence interval. But whenever you have a like a target variable, it is always suggested to go for the supported regression machine, and so that will imply the principle of structural risk minimization, which is based on both empirical as well as a regular loss function. And yes, as I was saying, like these points are my support vectors. Whenever you have a let us say less number of observations, this data, it will imply some artificial variables, and it will increase the data dimension, and then we can do the modeling. Yes. Yeah. Okay. In case of any machine learning techniques or artificial intelligence techniques, we have user-defined parameters, because if you run the machine learning model now, and if you run after 1 second also, that model will give us a different result, because we choose a different parameters for that, and these parameters are the user-defined parameters. We need to choose these parameters in such a way that the final error should come less. So, but whenever you run the classical time series or statistical models, if you run now and if you run after 1 year also, it will give you the same result, because they are all based on certain assumptions. But the machine learning models, even after next run itself, it will give you different results, because these are all user-defined parameters. As I was saying, in case of Maclaurin-Pitts model, we need to define our parameters in such a way that the error should be minimized. We need to choose a cost function lambda and this epsilon function, and we see there at a different time, and we can, and so only the what we do is usually in case of machine learning, we go for the different cross validation scheme. We divide the data into 10 parts, and we build the model for the all these 10 parts separately, and we combine these all these models, and we take the average of the values, and then we can say this is a finely fitted model. So only, like, it is not necessary that machine learning models are always better. We need to choose the model based on the nature of the data, and we need under machine learning techniques, we need to define the user-defined parameter in different parameter. We have to try. Now, whenever we are getting the error or less, that we can consider the final hyperparameters. So this is all about these two models. I dealt in details about the artificial intelligence, and there are some other models like VAR models. Suppose we have two variables, they are correlated in nature, we can go for VAR model. Then we have suppose you have uncertainty and you have some information on that, we can go for the Bayesian time series models, and then we can go for XBAR. GARCH models are there for the nonlinear data, and then we have INR and SPINAR models for count data. We have CART, random forest regression. We have different deep learning techniques, fuzzy techniques, granular. Suppose if you want to do some granulation to the neural network, that granular neural networks are there. Like that, we can use different models based on the nature of the data, right? So what I will do is, any breeders are there in this group, Kapil? Any biological other breeders or any other scientists, other students in this?
Yes, sir. Breeder are there.
Okay. So whatever I explained as of now, those all for the this time series data. And suppose if you have a time series data set, then we can use this enable me to share the screen.
So now you can share.
My screen is visible now.
Yes.
Okay. Yeah. By using artificial intelligence techniques also, we can develop the genomic prediction models. And here in our institute, we are working on this. So you, as you know, all like we have in breeding population. So again, like as I explained in time series also, we need to divide the data into training set as well as a testing set. And in the training set, suppose we have a 200 lines. In the 200 lines, we divide them into, suppose, let us say a ratio of 90 to 10. Suppose 190 lines we divide for a model building and remaining for a validation part. And for the 190 lines, we need to have both genotype data, SNPs, and as well as the phenotypic data. And for the genotypic on this training data set, we build the model. And for those 10 lines, you predict the performance of the you predict the performance of phenotype. Let us say the genomic estimated breeding values, and this breeding values you see for the cross, and then you can for example, in case of a hybrid race or a hybrid program, so you can predict the future crosses and you can avoid the F2 or F3 generation, and you can, by using this genomic predicted values, and you can avoid those and you can develop the varieties in a quicker time. So, and in case of genomic prediction models, like we have different models. We have classical models and artificial intelligence models. In classical models, we have a linear mixed model like blurb, G blurb, and then we have a probability based blurb, and then we have a Bayesian models, base A, B, C. Then we have a regression models, lasso, ridge regression, elastic net, and then we have kernel based models like the reproducing kernel input space RKHS model. And then we have artificial intelligence models like random forest, support vector regression, as with ANN, deep neural network, CNN, DPN, RCN. These are all different models can be used for genomic prediction. And this is for the basic structure of genomic prediction, where you can, as I was saying, like you divide them into training part and testing part. Once you have SNP data in the training part, that data can be converted into the your numeric form by, and that numeric data again can be converted into a genomic relationship matrix, GRM, and that matrix you consider it as input like a regression, and then you develop the model, right? So these all again the AI-based genomic prediction models. So these all models we developed in our institute here. So this is structure of that, and I will just explain it with one example. Yes. This is one data set, like we have a 312 lines of the rice RDP population, and this has been grown in 3 environment in 2 years, 2017 and 2019. Nitrogen recommended, nitrogen 15, nitrogen low, nitrogen at a higher form. And then we have SNP data set, and this SNP data set has been taken from rice biodiversity website, and based on this we developed the genomic relationship matrix, and finally we built these models, and it has observed that the artificial neural network has performed better compared to other classical models in genomic prediction. So this I just wanted to show that it is not only like we can employ time series, I mean, neural network in time series. You can employ artificial intelligence, even genomic prediction also, and we can predict the genomic estimated predict values also. Okay. So next part is hybrid time series modeling. Like whenever suppose we say we have two parts in the, suppose sometimes the data will be contained both linear as well as not. So whatever I explained about the classical time series and neural network artificial intelligence here. For linear time series, you can use a time series models, and for the non-linear part, we can use a your artificial intelligence model. But sometimes what happens, your data contains both linear as well as a non-linear part. Under such condition, we need to go for the artificial intelligence models. If you see here, suppose I have actual series, and this I divide into linear component and non-linear component. Non-linear component is basically my residuals, and then I have for the linear component original data, I employ this ARIMA model, and then I will check the diagnostic checking of the model, and in diagnostic checking, if the residuals are correlated, then I employ that this artificial neural network, and I will fit the artificial neural network on the your residuals, and this fitted model again I will combine in aggregation part, then I can generate the final forecast. So this is a methodology of the hybrid modeling, or so-called two-stage modeling. So like that, this is the ARIMA support vector regression modeling, where in first part I apply the ARIMA model, in the non-linear residual part I will employ the support vector regression part. And this is again for, in case of long memory, this is one of our publication where like in case of the data was long memory, again the residuals were significant, then we employed this artificial neural network on the residuals, and we fitted the model, and where we have given the final forecast, and it is better than the predicted one. Similarly, this is with respect to a wavelet and ARIMA hybrid methodology. Yeah, this is with respect to Arimax and ANN supported machine hybrid methodology. And in case of special temporal model, also we have developed some hybrid models where for the first part we had developed the Sturma model, and the second part was significant. The residual were significant. We built the support vector regression and ANN model on that, and this becomes the special temporal hybrid methodology. This is for one of the paper where we have done the combination of wavelet and artificial neural network, and this is also part of the hybrid methodology. So this is all about the time series in the artificial neural network, artificial intelligence models. And these all models, whatever I have explained here, those all we have employed in our data, and we have made some publications. This is one of my students' paper where we have developed some AI models for predicting the water stress drought in the Hyderabad region. And here we have employed we have converted the we have calculated the SPEI. And in this SPEI, we have forecasted using the different artificial intelligence models, and here supported regression has performed better compared to the other models. And similarly, in one of our publication, we have developed a model for forecasting oil seal production of India. And simply here also the supported regression has performed better compared to the neural network model. And this is, as I was saying, like tuning. So like user-defined parameters in case of machine learning, the hyperparameter optimization becomes very important steps where it depends on the it leads to the changes in the accuracy. In this one paper, we have developed the scheme for tuning the supported regression parameters, and this was done for forecasting the cotton production in the country. And here again, this is we employed ARIMA neural network for forecasting the drought. And then again, as I was saying, like light trap data. So this is one paper where we have employed some count time series models and artificial intelligence models for predicting the light trap of rice gallmeal population in different parts, hot spots of the country. So then, as I was saying, like model parameters, we can estimate even using the genetic algorithm and optimization techniques. And this is one paper where we have estimated the parameters of ARIMA using genetic algorithm, and we have estimated the model parameters and forecasted the maize yield. Similarly, this is we have developed a hybrid model for modeling and forecasting the banana production. And as I was saying, like whenever you have a intervention time series, suppose the government of India has announced the lockdown on 25th of the March, and that after that we have developed this paper for the whether the COVID-19 impacted any has any impact on the supply and demand of the rice prices and arrivals. And this is the one paper we have developed for the this is for the tomato and for the Hyderabad region. Similarly, we did one study for even rice also. So this all we employed the artificial intelligence based intervention model and we did the modeling. And this is one for the, this is a combination of ANN and WNN. Here again, ANN is VM. And we have one model for long-term forecasting of crop yield. Then we have our RPO model, and we have developed the special temporal model for forecasting special temporal temperature. This is again the for special temperature using some fuzzy techniques. And this is the one model we have developed two-stage special temporal time series model for forecasting rice yield in Andhra Pradesh, where we have taken 13 districts yield, and I have developed the correlated weight matrix in this. And based on the correlated weight matrix, the two-stage special temporal model was developed. This is for hybrid spatial temporal modeling for space-time rainfall forecasting of northern West Bengal. So here also we have developed some hybrid spatial temporal model. So these are all about some examples, and based on my experience and based on the slides which I present here, I can clearly say that no model is universally accepted for all the data set, and you can call it as a no free lunch theorem. It states that no single statistical machine learning algorithm is universally the best algorithm. Suppose there are two statistical machine learning techniques, A and B. There will be as many as situations in which A is worse than B, and there will be as many as situations in which B is worse than A. So we cannot say that artificial intelligence always performs better. If the data is linear and simple problem, then your ARIMA model will always perform better than the neural network model. If it is a complex data set, your neural network model will perform better than the ARIMA model. So we should not say that whatever the model I develop, that model will perform always better than the other data set. So the model development always relates to the particular data set. So we should not say that whatever the model, like you can say in some extent that this model may work, but you cannot say that this model will 100% work for all the data sets. So it is my suggestion is that whenever you have the data under consideration, we need to employ different models, and you need to choose the right model for your particular data sets. Okay. So finally, yes, I can conclude like we need to choose the model based on the nature of the data, and there are different models available, different category of models available for the data set, and whenever based on the data under consideration, we need to go for the different models. And if you are interested in time series, there is one paper by Robert Hinman, though it is a very old paper, but recently also there one more paper has come, the 25 years of time series forecasting. This is published in International Journal of Forecasting, very reputed journal. So if you are beginner in time series, you can go with this paper. This is very important paper. We'll come to know under which condition which model has to be employed. And then we have this Jang paper is very important. This was the first paper in time series for neural network, and this paper you can read. And we also have some papers. If you're interested, you can go through these papers, and you can employ these some of the models which I explained here. And this model can be implemented in your R package using all the packages like T series forecast, FNALIGAP, LM test, neural net, ELM1, NNFOR, E107, STRMA, SPDEP, and fraction diff. These all packages can be used to develop the models which I explained in my class. So thank you. So if you have any doubt now, you please ask, and then we can go for the further practical class for some 15-20 minutes. So if anybody has any questions or anything, then I'll be happy to explain.
Good afternoon, sir.
Anybody has any question?
Good afternoon, sir.
Good afternoon, please.
I have a doubt.
Yeah, tell me.
Sir, am I audible?
Yes, you are audible. You are audible. Please ask.
So, like we use artificial neural network, random forest, and support vector regression for prediction. Can we use PDN and Poisson deep neural network and K nearest neighbor for prediction purpose?
Definitely, that is what I am saying. You can use n number of models, but again, it depends on the nature of the data, and we need to choose the whatever the artificial intelligence models you choose, the activation function or the kernel trick function depends. Like suppose the data is count, you need to choose the suitable activation function. But people, what they will do is generally generally it is trend that we don't see the suitable activation function or the kernel trick. We directly use different models, and among the used model, whichever model is giving us the better result, that model we call it as a final model. So that is what, like the machine learning, like we need to choose different models and we need to identify the best model. But I cannot say, or you cannot say, like this model is always right, or KNN is always better, or The TDNN is always better, or the Poisson based model will be, suppose you have a data like count data
Yes,
and
sir. I
insect
have
pest data,
count
and
time series data.
yeah,
Insect
yes,
based data I have.
that is
So
what.
can I apply that model?
Count data, you can choose the your sig model activation function, then it will give you better result. Poisson activation function, like sig model activation function, will be more useful.
Thank you, sir.
One question from where we can learn about these models in details. Yeah, this is again see, these are all the different models. We can, the most of the literature is available in the internet. Like for a time series, basic time series, you can go for Box and Jenkinson book is very important. And otherwise, there are an ISRA website. There are a lot of materials materials are available on the website. You can read them. Or else, recently last year I have organized one training program where most of the videos are available in Telegram. That videos also I can share, and I have a e-manual. So e-manual is freely available. Those in this manual we have almost like all the models of time series we have explained, even not only time series, but most of the breeding or other problems also, models, stability, the genomic, the gene interaction, path analysis, all these things we have given in that manual. So I will share that manual with you, and you can go through that. Even R codes, everything is given in that, and you can read that material. Okay, if no more questions, okay, I can go for the practical demonstration.
Okay, sir. Okay.
Okay. Wait, madam, class ಮುಗಿಸ್ತೀನಿ. ಅಲ್ಲಿ ಕೂತ್ಕೋ. My R screen is visible, Kapil?
Sir, yes, sir. It is visible.
Okay. See, for this practical demonstration, I have taken the rainfall data of Kerala. This code and the data set I will share with Kapil, and even slides also you can take from later. You just quickly see like how this model will perform. So to this do this practical, we need this many libraries. Forecast package is required, E1071 T series. ggplot2 is required for plotting some graphs, and then we need tidyverse for arranging the data. fnonlinear package is required for completing the PDS test, and then we need LM test for seeing whether the models or parameters are significant or not. Right? So I'll just quickly run them. So these all libraries are installed. Okay. So you can clear the console. Then set the session to the set working directory to the source file location. I will import my data now. So this is my, if you want to see the data, you can just simply type G. But sometimes what happens, the data numbers will be more, the console will be full. So it is better if you want to see the data, just simply type head of G. So first 6 observation will be visible, right? And if you want to see the last 6 observation, just type tail of G. The last 6 observations will be visible. So I have 1420 observations in the rainfall data now, right? So as I was saying, like any for any modeling task, the first step is in time series is first we need to see the box PS test, whether the data is correlated or not. So for that we have a test called box.test, and G is my name of the data, and rainfall, if you apply the data dollar sign here, for example, if you test box.test, the function will come automatically. Just double click on it. G is my name of the data, then dollar, and rainfall is my data set. Just press here, enter. And if you see the probability value, it is less than 0.001. I mean, it means the data is highly correlated in nature. So whenever the data is correlated in nature, we can say we can go for the time series modeling. So the next is once then we need to, as I was saying, like once the data is autocorrelated, we need to see the plot. If you can just see the plot here, this is my time series plot. This can be developed by using the ggplot function of the ggplot2 package. And this is my time series. And by looking into it also, we can say the time series under consider is highly nonlinear in nature. And whether it is nonlinear or not, if you want to confirm it, just do the BDS test. BDS test is available in F nonlinear package. And M equal to this is the data dimension. The data will be divided into 3 parts, and the non-linearity will be calculated, and these 3 parts again the sampling will be done, and this your standard deviation statistics will come here. And if you see most of the parts, the data under consideration is non-linear in nature. Whenever the data is non-linear in nature, it is better to go for the neural network or any time series model, I mean artificial intelligence models. And then again, like you see the dimension of the data, I have 1428. What I will do is, as I was saying earlier, like we need to divide the data into training and testing part. So here I will take first 1 to 1416 observation as my training part. So this is my training data. And I divide I will take remaining last 12 observation like 14172 to 1428 as my testing part. So this is my testing data. So A1 is my training data and A2 is my testing data. If you wait for some time, yes. And if you want to see again whether there is a correlation in the training part or not, you just do the box PS test again. The data under consideration, your training data is also has a autocorrelation in it. So once the autocorrelation is there, we need to plot the ACF and
Sir, you are
ACF.
not audible.
If you see, which I am not audible. Am I audible, Kapil, now?
Yes, yes, अभी ठीक है sir. ठीक,
Okay.
continue.
Okay. Kapil, can I take 2 minutes break? I'll just come back, huh? Just 2 minutes.
No problem, no problem, sir.
Okay.
Take. Sir, please unmute.
Okay, Kapila.
Okay, now it is okay.
Okay. Yeah. Okay. See, as I was saying, like we have to divide the data into training and training and testing. You can see the again workspace auto correlation is there in the training data now. And if you see
Sir, please share your screen, sir.
Achha. Okay, screen is visible.
Yes, sir. Yes. Now
If you see the PSEA plot here, there is some seasonality pattern is existing in this. If you want to see this for like more lags, you can just simply type in that lags report. ACA plot, there is a clear indication that the data is a monthly seasonality is existing in the data set. And before going to the modeling, we need to deseasonalize the data and we have to go for the modeling. So this can be clearly indicated in the ACA plot. So not gone into that part because seasonal RMI is another topic. And so, but whenever you have a such kind of data, monthly data, it is always better to see the seasonality and we have to deseasonalize the data and then we have to fit the model. Right. So as of now, as I explained, like whenever you have the data, we need to see the autocorrelation test, and then we have to go for the time series plotting, and we need to go for the BDS test for whether the data is nonlinear or not. And once these two conditions are satisfied, then we need to go for the model building. Now there is a package called forecast package in ARIMA that is there. We have a function auto.arima. So up to 5 lakhs, that model will take automatically, it will select the model orders, the combination of 5 AR and 5 MA orders, and it will give the model directly. For example, if you type M1 is a model name, you can assign any name here. Auto.arima. If you type auto.arima and give the name of the data series, see this model has come. And if you want to see whether the parameters are significant or not, it has given me AR4 and MA2. So my model is here. My model is here 412. So the basically originally the data was non-stationary. Then it has taken one difference, and the data has become stationary. And then it has taken 4 autoregressive order and 2 moving average orders. So most of the cases, this all the parameters are significant in nature. So if you just simply type M1 or summary of the model, the significance of the models will not come. For that, we need a function called COEF test. It is available under the LM test package, and that function will help us to whether the parameters are significant or not. So as I was saying, the next step in any modeling is whenever the model is fitted, we need to see the diagnostic checking for the residuals. So here we have a test called box.test, and M1 is my model name, and residuals are in the models. So you can just type yourself also here box.test, it will come. Then M1 is my model, and $sign, you choose the residuals. So if you see here, the residuals are significant in nature. So it means there is some information is left over in the model, and this whatever the model you have fitted, this model is not a proper model, right? So it means we either we can correct this model by using the hybrid model, or else you can choose some different models, right? So this is the ARIMA, and the model is fitted. Now you want to see the fitted values, like what is the predicted values of the training data sets. This function fitted, if you type M1 $fitted, the fitted values will come. And if you want to import them into the Excel sheet or CSV file, I export into the CSV file, write at CSV, as you have to create them into data frame, and this values will come outside. So you can just type ARIMA fitted. So these are my fitted values, right? So I can get the fitted value like this. So now what I will do is for the training data, I have the fitted value. Now I will forecast the value for the testing data set. I left 12 observations in the testing data set, and this my chip I will forecast for the next 12 observations. And for that, I have a function called forecast. and these forecasted values can be taken out, and I compare this forecasted value with the actual values, and I have derived in my RMS is for the testing data set, it is 222.63, right? And if you want to export this also, you can export by writing ARIMA forecasted, right? The values will come out. So now the ARIMA model has over. Now we can go for the ANN modeling. So ANN, we have a function called NNET. If you just go to the package here and forecast package. So this is my forecast package. In this forecast package, I have many different functions. And in this one function is there, that is NNTER. This function. If you click on this, these are the descriptions, and some example data sets also will be given here. And if you can see here, like it will ask me the input lag, a numeric vector of time series, and I have to give the input lag in terms of p equal to 1 if there is no seasonality. And this is p, the small p is my input lags, my size is my number of hidden nodes, repeats equal to 20, the entire network is repeating 20 times. If suppose I have some exogenous variables like temperature or other variables, that also I can give in the model in terms of the X-ray. And these are my user defined parameters, and this model can be built. So here what I have done is I have taken the input variable and I have taken the 6 input lags and 10 hidden nodes. Okay, so I will run this model. So my model has completed, and this is about my model is with a 6 input lag and 10 hidden nodes, and the weights are 25. But whenever you build the neural network model, the problem is like most of the time we make the mistake of underfitting or overfitting. So whatever this average network weights are 25 network weights are, sorry, here 81 weights are there. This weight should not be more than your number of observations. It should be at least 50% less than your number of observations. For example, here we have 1420 observations. So my weights are 81, right? So like this, we have to see, and we have to choose the different lags and nodes, and we can choose fit the model. So what another option for this is you can directly, instead of defining all these, and this is, since it is auto model, like auto package, it will choose the parameters, best parameters by itself. You can just directly type M3 model 3 equal to NNER A1, and it will give us the direct model parameters. So this is my M3, and M3 to see, it has given me 393 weights. The model which I was developing earlier, it was underfitted. So now I have a 393 weights. It has taken 26 input lags. It means the data has a little bit long memory, and it has taken 26 lags, and it has taken 14 hidden nodes to process the data. So like that, we can build a model, and you can choose the different parameters, and you can compare the efficiency of the model. So what I will do is I will just simply see the accuracy of the model. You can note down, like in case of here ARIMA, our error was like 164. RMSE was 164 in case of ARIMA, and yes, I will see this M2, and accuracy of M2 is 108. So from 164, now the fitting error, the training error has reduced to 108. And just if you want, you can just export this data again outside, and sort of like run the. And for the testing data set, it has given 268 RMSE. It is more compared to the ARIMA model. Sometimes what happens, your ARIMA training model will be better, but your testing will not be good. So again, you need to choose a different user-defined parameters, and you have to choose the right model. Right? Then we have M3. In third model, it is we are building it automatically. Yes, and third model has given us RMSE of 50.45. So from 164 to we have come down to 50.45. Our error has almost reduced 3 times. So right. So again, you can forecast this also. Here my forecasted error also has reduced to 202. But in case of testing error, it was 222. But now with the proper hyperparameters ANN, it has reduced to 202. So if you want, you can take out these residuals outside, right? And similarly, you can build a support vector regression model also. As I was saying, like in case of support vector regression, it is a supervised learning. We need training as well as a testing level training input vector as well as a target variable. What I have done is, since I don't have a target variable, for today's temperature, I have taken rainfall. Tomorrow's rainfall, I have taken, next month rainfall, I have taken as a target rainfall, right? So from 1 to 1416 is my training input vector, and 2 to 1417 is my target variable. And similarly for testing data set also, 1416 to 1427 as my testing variable, and for 1416, 1417 will act as my target variable, right? So like this, you can give the target variable. And suppose some people, what they will do nowadays is, target variable, again they will employ the ARIMA model, they will predict the target variable, and the predicted target variable they will give for the support vector regression. That also can be done. So now I will run the support vector regression model. This is available in E1071 package. My M4 is my support vector regression model. These are the user defined parameters. You can choose different parameters also. I can get the fitted values, and my fitted value is 188.968. So it is again more than the neural network, right? Because we need to choose the right parameters, and we have to see which model is performing better. Right. So yes. So and oh. And this is, as I was saying in theory class, that we can compare the results by using a DM test. So DM test, dot test is a dipole Maroney test. You can see the model comparison by using this. There is a significant difference between the model 1 and model 2. And again, there is a significant difference. I mean, you can run this. You can clearly say that model 1 is sufficiently different with respect to the model 3. And this is also given us a lesser error. So we can say that the neural network model has performed significantly superior with respect to the your ARIMA model, right? So in earlier, like we seen that our ARIMA errors, they were auto correlated in nature. So it means the residuals has some information. So we can see here R1. I will take out the residuals M1, the dollar residuals. The residuals will become out. Then what I will do is, I can see the box dot test. The R1 here. So I can say that residuals are significant. So it means there is some information left over in the data. So that can be corrected using the hybrid model. So what I will do for this, and I will see again whether these residuals, they are non-linear or not. Obviously, they are non-linear in nature. If you are employing this PDS test here, and now what I will do is, I will build the neural network model on the residuals. So you just see here, this NNETR, R1 is my residuals. I am building the residuals neural network model on the residuals. Once this model is built, then the fitted values of these residuals, I will combine them into the ARIMA fitted values, and then I can compare the forecasting error. See, my model has built, and this is my fitted values. I will take what I am doing here. This N1F is my fitted values, fitted residuals. This fitted residuals I am combining with the ARIMA model, ARIMA fitted values. N1F I am combining with the M1 fitted is my ARIMA fitted values, right? So I am combining them. I need to do these corrections because what happens, like in neural network, it will take different lag for different data sets. So for the original neural network, it has taken 24 lakhs, but here it has taken the more lakhs. So to make it equal, I will take the data from 32 to 1416. This may not be constant always. This we can see the how many lakhs it has taken, and you can divide the data and you can make the equal. To compute the error, the data need to be equal. So I have I have commanded build the hybrid model now. Then I will compare the performance hybrid model with respect to the ARIMA model, right? So my hybrid model has given me the error of 39.18. So finally, like the ARIMA has given 168, the neural network has given me 50, and the hybrid model has given me a error of 39.18. So like this, we can do the modeling, and you can see but this modeling result may not be true for all the data set, because it depends, obviously depends on the nature of the data. And you can see the comparison again if you want to see this is like finally my error has reduced to the 39. And if I want to see the fitted plot, this I have one separate data set. For this I'm fitting the plot by using the ggplot2 package. These are my different models. We create the data set in the single column. Then this is my fitted plot. So this is like this for your data set. Also, you can draw the fitted plot. This is one data set where in that my published paper I was explaining, like this is a before COVID period and this is after COVID lockdown period. So this is 25th of the March. Government of India has announced the lockdown. Before the supply, the arrival of the this tomato was more, and later when the government has announced the lockdown, it was less. So this is a clear difference between the pre-COVID period, pre-lockdown period, and post-lockdown period. Under such condition, your normal ARIMA model will not work. You need to go for the intervention time series models, right? So this is all about the practical. These two codes and data and other slides I will share with the couple. You can take with me. So if you have any doubt, you can ask me.
So the session is for discussion, open for discussion. If anyone has any doubt, you can ask.
Yeah.
So can we calculate R square value for this in an SVR in R?
Yes, this is a good question, because see, R square is we generally compute for the statistical models or time series models where we have a model parameters and distributions. And for these models also we can compute the R square, but R square we can compute because we are not getting total sum of square. We are not getting any decomposition sum of square here. So R square is not a good measure. So R square, though you can calculate it for between your actual and predicted values, you can calculate the R square. But according to my opinion, for machine learning models, you should not go for the R square. The RMSE, mean absolute percentage errors measures, are always better than the R square. So R square will be good whenever you have statistical distribution based models.
Thank you.
This is one question, sir. Kindly add PLSR model package if possible for hyperspectral image processing. Now, this hyperspectral image processing again is like different topic. So there are people, like if you want some more detail on this, there is one Dr. Naveen. He is my friend, so I will give his contact to you, so you can discuss with him. He is doing more on hyperspectral image processing, because image processing again it is a different topic, so it is totally different from the this time series modeling.
So, sir, we really appreciate the time and effort you put into preparing a detailed and helpful lecture for us. We consider ourselves fortunate to have had the opportunity to learn from the eminent professional like you. And sir, your presentation was not only informative but also highly engaging to all the participants. In conclusion, we express our heartfelt gratitude to Dr. Santosha Rathod sir for delivering an outstanding presentation on machine learning techniques for modeling agricultural data. So thank you very much, sir.
Thank you, Dr. Vijay and Dr. Kapil for giving an opportunity. Thank you very much.
Now I kindly request the participant to share their training experiences and provide feedback for further improvement.
Oh, I will log out. Dr. Vijay will log out from the session, right? I will
Yes, sir. Yes, sir. Yes. Sir. Thank you.
Okay, you can leave.
Yes.
Hello, Vijay.
Yes, sir. Yes, sir.
Am I audible?
Yes, sir. Audible, sir.
Okay, okay.
Sir, it's
first of-
possible to
Yes.
show your video also, sir?
Actually, okay, I will.
Otherwise, no issue, sir. You can share your views.
No, something technical problem because I'm online in my mobile and in mobile some technical problem arise. Okay.
No issue, sir. We can hear you, sir.
Uh, I first of all congratulate all host Dr. Kapil and Dr. Vijay for successful completion of the 5 days training program. Really, I enjoyed a lot. I shared about the R with you, Dr. Vijay, with you in
Yes, sir.
IRI.
Yeah, yes, sir. Yes, sir.
And you provide a great opportunity so that I participated in this training program and I enjoyed a lot since I learned many new things not only for our software but also statistics like many things one guy came na Greej Jha sir
Ah,
came one
yes,
day,
sir. Yes, sir. Yes.
and I learned a lot about the correlation, regression, and since those things we learned from our graduation, but this training program revised those all things and how we use those things in our research for better analysis and interpretation. This training became very useful for me, especially for me. This training is very useful, and some things which need some improvement. But I
Yes, sir.
think in online mode and in 5 days, those improvement is inevitable because in 5 days you can't uh, uh, teach all those things to us. So let's leave those things. And lastly, I once again congratulate and best wishes for all Dr. Vijay, Dr. Kapil, and all participants. Okay, thank you.
Thank you, sir, for your valuable experience. Uh, anyone? Siaram, am I audible?
And I once again remind Dr. Vijay, please share the augmented design and their data format and code because recently a lot of project I received from NVPGR and in all those augmented design I have to execute.
ओके ओके सर, आज शाम को आपको भेजता हूँ सर मैं.
Uh,
ओके, थैंक यू. Mahavir, Siaram, anyone from the participants want to share their views? So finally, we are like about to close the training, and we, as a organizer, we thanks to all the participants for their cooperation during the training program. And definitely, all the video lectures are available, will be available on YouTube channel, so you can anytime watch them and practice all the exercises which we conducted in this training session. And we thanks to all the resource persons like Dr. Girish Kumar Jha sir for correlation and regression analysis, Dr. Rajiv Ranjan Kumar sir, Dr. Santosha Rathod sir, Dr. Rahul Banerjee sir, Dr. Bandita Kumari sir, Dr. Nitin Vasne sir. We very thankful to them for their lectures, and I thank to all the organizers, Dean College of Agriculture, Vice Chancellor, Agriculture University, Jodhpur for providing this opportunity to conduct this training to all the participants. So thank you one and all.